A very good afternoon to all the people who are connected with me here today. I am Aanchal Alagh, a PhD student from Universitat Rovira e Virgili in Tarragona, Spain. Today I am going to discuss a part of my PhD work which is on 3D assembly of tungsten disulfide nanomaterial for H2S gas sensing application. This is the outline of my talk today. I'm going to start with a brief introduction where I'm going to talk about the importance of H2S gas detection, followed by properties of next generation material for gas sensing. Then I'm going to discuss the two-step synthesis process which we have used for tungsten disulfide synthesis, followed by sensor fabrication. Then I'm going to discuss some of the results from material characterization and gas sensing. Finally, to wrap up, I'm going to conclude with the future work required. H2S, which is commonly referred to as hydrogen sulfide, is known by several other names such as sewer gas, manure gas, stingnem, hepatic gas, etc. It is a colorless gas which is heavier than air and tends to accumulate in low-lying areas. It is naturally produced by bacterial breakdown of organic matter and as a byproduct from industrial activities. Depending on the concentration present, it has a characteristic odor. For instance, at concentrations below 5 ppm, it has an offensive odor similar to that of rotten eggs, whereas at higher concentrations of 100 ppm and above, it deadens the sense of smell, which makes it as a silent threat for potential victims. Moreover, at higher concentrations of 100 ppm, the gas is highly poisonous and acts upon the human nervous system, which could cause paralysis, and with prolonged exposure, it could even cause immediate death. Therefore, the acceptable concentration is kept in only parts per billion. Aside from the harmful health effects to human bodies, wet H2S can even corrode carbon, steel, and other metallic surfaces, bringing out economic losses. Hence, it is necessary to constantly screen H2S gas and limit work-related danger. In this respect, for gas sensing applications, 2D layered nanomaterials analogous to graphene, such as transition metal dichalcogenides, have emerged as potential candidates for improving the gas sensing properties. These transition metal dichalcogenides are represented by the chemical formula MX2, where a metal atomic layer is sandwiched between two atomic layers of a chalcogen material. Among various two-dimensional transition metal dichalcogenide available, tungsten disulfide has attracted major attention as it offers high surface to volume ratio, inherent flexibility with superior semiconducting properties, low power consumption, and high compatibility for integration with conventional silicon technology. However, in spite of all these interesting properties, research on tungsten disulfide nanomaterials for chemical gas sensing, particularly for H2S gas, is very scarce. This is because of the greater difficulty in controllable growth of tungsten disulfide, which is attributed to the higher melting point of tungsten precursors, which is the motivation of this research work. So here we have synthesized multi-layered nanofilms of tungsten disulfide in two steps. In the first step of synthesis, tungsten trioxide nanoneedles were directly grown on commercial alumina substrate via aerosol-assisted chemical vapor deposition process. The substrate was kept inside the hot wall reactor at a temperature of 400 degrees Celsius. Then tungsten hexacarbonyl dissolved in a mixture of acetone and methanol was sonicated and placed in an ultrasonic bath to convert the mixture to an aerosol. Nitrogen gas was used as a carrier to transport the aerosol to the heated zone inside the reactor. The duration of the whole process was 30 minutes, and after the deposition, the sample was annealed at a temperature of 500 degrees Celsius in synthetic air. In the second step, tungsten disulfide was synthesized by the sulfurization of the grown nanomaterial of the grown tungsten trioxide nanomaterial using an atmospheric pressure CVD technique. For this, two boats loaded with sulfur powder were kept at different temperature zones of the deposition furnace, whereas tungsten trioxide sample was placed at 850-degree temperature zone in the downstream of the argon flow in the quartz tube reactor. as shown in figure B here. The initial step of sulfurization process goes for a span of 30 minutes, wherein the sulfur powder at the 850 degrees Celsius zone sublimates. The total time for deposition is kept at 60 minutes. Here is the picture of the commercial alumina substrate used and the fabricated sensor. So the substrate comprises of interdigitated electrodes on the front side and a platinum resistive heater mender on the back side. The heater mender is characterized to set the operating temperature of the fabricated sensor by applying external power supply. As shown in the two figures here, picture A, the green color is the sensor transducer with deposited tungsten trioxide nanomaterial, which is thermally annealed, which after the sulfurization process changes its colors to the black color. Now, after the synthesis, the grown nanomaterial is characterized using scanning electron microscopy and Raman spectroscopy. As shown in figure A, tungsten trioxide grown by AACVD technique consisted of thin and elongated nanoneedles which were randomly oriented. After the sulfurization process, the morphology of these nanoneedles changes completely to form a continuous film of tungsten disulfide having a mixed morphology of nanotriangles and nanoneedles. Then from Raman spectroscopy, two spectrum were observed. In the lower spectrum, all the peaks indicates the formation of monoclinic tungsten trioxide phase, whereas in the upper spectrum, the two main Raman active modes for 2H tungsten disulfide at 348 and 414 were found. In addition, two broad peaks at 700 and 803 were also detected with a low intensity compared to tungsten disulfide spectrum, indicating the presence of some tungsten trioxide impurities. The four graphs here shows the gas sensing characteristics of the fabricated sensor towards different concentrations of H2S gas at a constant operating temperature of 150 degrees Celsius. When the sensor is exposed to H2S, which is a reducing type of a gas, the resistance of the device increases, which indicates that our fabricated sensor behaves as a p-type semiconductor. The gas response is calculated using the equation given here, where R gas corresponds to resistance of the sensor in presence of H2S gas and R air corresponds to resistance of the sensor in presence of synthetic air. The sensor response was calculated to be 53.05 towards 40 ppm of H2S gas and decreases down to 15.6% when the concentration is reduced to 5 ppm. In graphs C and D, the sensor was tested at 3 and 4 different concentrations of H2S at a constant operating temperature of 150 degrees Celsius. For this measurement, a diluted mixture of H2S in dry air was injected for 10 minutes in steps of increasing concentrations from 300 to 800 ppb in case of graph D and from 800 ppb to 5 ppm in case of graph D. Exposing the sensor to lower concentrations of H2S gas revealed the gas detection limit of the fabricated sensor is 200 ppb at 150 degrees Celsius. From the results, it is quite evident that there is an increase in response with each increment in analyte concentration. Finally, to conclude, we have shown direct growth of tungsten disulfide nanofilms on the sensor transducer. Then we have fabricated a chemoresistive gas sensor for H2S gas sensing at low operating temperature with lower detection limit of 200 ppb. The results obtained demonstrates better sensing performance of the fabricated tungsten disulfide nanotriangles and nanoneedles hybrid. This is attributed to the 3D assembly of two-dimensional nanotriangles and one-dimensional nanoneedles of tungsten disulfide, which offers more interface with higher adsorption sites on edges, resulting in availability of abundant active sites for gas interaction. Moreover, Multi-layer nanofilms offers more electron transfer channel for improved reaction between the material and target gas. In future, we intend to study gas sensing characteristics of the fabricated sensor for H2S gas in humid environment and at lower temperatures. Finally, I would like to thank my research group in Tarragona and the funding that we have received for this research work. In the end, thank you for your attention.